MIG Welding 101 for use in teaching Stage 5 Industrial Technology Metal. This MIG welding presentation contains an introduction, how welding works, parts and equipment, welding safety, setting up work, setting techniques, and assessing welds. The MIG weld process has 7 main parts. The power supply provides electrical power to run the process. The welder itself receives power, wire, and gas and controls the flow rate of wire, electricity, and gas depending on the settings chosen. The gas supply is an inert mix of usually argon and carbon dioxide, but can vary depending on the requirements of the weld. The welding wire acts as a positive electrode in the welding circuit and adds material to the weld pool. The earth clamp completes the circuit when the welder is activated. Without the earth lead making an electrical connection to the workpiece, the process will not start. The MIG gun handpiece is used to direct the wire and gas onto the weld. It also houses a trigger which activates the welder. The workpiece is the main part being welded. The workpiece must be held securely so it does not move. It also must be connected to the earth clamp or be in electrical connection to the earth clamp through a steel bench, for example. How does it work? Welding works by discharging an electrical current between two electrodes, the welding wire and the workpiece. This discharge of electricity generates temperatures above 3000 degrees, which melts the workpiece and the welding wire together into a pool of molten metal. The metals mix as a liquid, then solidify together, forming a join. The weld pool is kept free of contaminating oxygen and nitrogen in the air by the shielding gas, which floods the weld area, displacing the air. Aside from the welder and its individual parts, other equipment needed for welding include bandana, helmet, long-sleeve jacket, welding gloves, long pants, leather boots, a dedicated work area such as a welding bay or movable screens to prevent others from the effects of UV radiation, clamps, and welding pliers. Welders do pose 4 significant risks to others. Number 1, electric shock. Welders discharge electricity between electrodes. If a welder is activated when a person physically links the workpiece to the welding wire, the electricity would cause a dangerous electric shock. In order to mitigate the risks associated with welding, users and bystanders need to be made aware of the risks and trained on how to use the equipment safely. Under no circumstances should a person be in contact with the workpiece and the welding wire if there is a chance the welder may be activated. If there is need to touch the welding wire for maintenance, the welder should be turned off and unplugged. Number 2, UV radiation. Electric arcs discharge ultraviolet radiation. This radiation can cause damage skin cells on any part of the body exposed, such as forearms, necks, bare legs, and even the retina inside your eyes if viewed without a protective tinted helmet. The only way to prevent ultraviolet radiation is to put a barrier between it and our skin. This is done with a welding helmet to protect the face, eyes, and neck. A welding jacket protects the torso and arms. Welding gloves protect the hands and overlap the sleeves so no skin is exposed. Long pants and boots protect the rest of the body. There is another risk from reflected UV radiation that could affect others not wearing PPE if the radiation reflects off a surface into the eyes of someone else. This can happen with reflective steel or even light painted walls. Care must be taken that reflective radiation is minimized where possible. Number 3, thermal burns. Welders can generate temperatures well over 3000 degrees. This heat direct from the arc can cause thermal burns, and the residual heat left in the workpiece, bench, clamps, or nearby material can cause burns for a long time after the weld has stopped. Thermal burns are the most common injury due to welds. Welds can spark and pop, showering nearby areas with molten hot metal. The heat coming off a long weld can heat up the leather gloves to where your hands get burnt inside them. Hot pieces, even after the welder is turned off, can burn through gloves, and when cooled in water can create dangerously hot steam. The best control for thermal radiation is to assume everything in a welding area is hot. Carry parts with pliers or vice grips and cool down hot welds as soon as practical. Thick leather welding gloves will give you some protection from the heat, and a bandana will prevent hot sparks nesting in your hair. Make sure cuffs are outside your boots and that there are no areas of your clothing that could potentially catch hot sparks. Number 4, electromagnetic radiation. A less common danger is that welders give off a large amount of electromagnetic radiation. Although not dangerous to most people, this radiation can interfere with the operation of some electronic devices, such as pacemakers or blood glucose monitors. Although not a safety concern, the electromagnetic radiation could potentially also interfere with devices, such as smartphones and watches. Although there may be some ways to prevent interference with medical devices in the context of this presentation, None of them are practical or authoritative. If you have an implanted medical device, do not weld until you consult the manufacturer. Butt welding is where two workpieces are joined end to end. There are two versions of butt welds. The first is to leave a small gap between the workpieces. This will be filled with weld from either side or both. The second way is to remove the edge of the material to be welded, creating an open V to fill with weld. As the weld penetrates the sides of the V, the weld pool replaces the material removed. If the weld is then ground flat, there is still full thickness of material left to give the joint strength. A fillet weld is used to join two pieces which are perpendicular to each other. If the welder can penetrate the thickness of the material, no material removal is necessary. If the material is too thick, an edge of the vertical piece should be removed to allow the weld to access the full thickness of the material. Usually, butt welds are ground flat and fillet welds are left proud. Settings. Individual settings may differ between manufacturers and will need to change depending on the metal, wire, and gas being used. Settings will need to change depending on what kind of weld is needed. It is important to be able to do a test weld and change settings accordingly. The voltage and wire speed knobs are usually placed near each other and will have a range represented by actual output in volts and millimeters per second or by numerical values assigned by the manufacturer. Some welders have a display showing what settings are. If you're not sure where to start, put your settings at the mid-level and work from there. There will be two dial indicators on the gas bottle. One indicates total pressure inside the bottle and the other indicates the flow rate of the gas governed by the regulator. Flow rate will depend on how much gas is needed to displace the air from the weld area. Gas type and mixture is governed by the material and wire being used. Mild steel uses a mixture of argon and carbon dioxide. Thin aluminium uses pure argon, whereas thick aluminium may include a mix of helium and argon. Many manufacturers and websites can provide recommendations for settings based on the type of material and thickness. This chart shows suggestions based on a range of variables. Whatever setting you use to start welding, it is important that you get familiar with what works and what doesn't, and how to adjust the settings to get an appropriate weld for its purpose. The techniques. The positioning of the welding gun has a huge effect on the quality and appearance of the weld. Because you are creating a pool of liquid, the way it flows and moves until it cools will change the qualities of the weld. Because the weld pool has high surface tension, it stays relatively close to where it is formed. That said, it is best to move your workpiece to a position where the weld pool will be formed directly above the joint, as shown in the flat position. Horizontal fillet weld. Techniques that may help in welding horizontally are welding in a pattern, effectively moving the tip in a repeating pattern as you move along. Triangles, loops, zigzags, and circles are common. Because every welder is slightly different, what works comes down to personal preference and practice. You can see in this video on the right hand side, I am welding, and because of the glare of the weld, you can't see what's actually happening. I've mirrored the movements I'm making on the right hand side on the left without activating the welder, so you can see what should be achieved. Vertical welds. Vertical ups and vertical downs can be the most challenging welds. MIG welders can go either up or down. The pattern may differ between user, but as long as the finished weld is strong, the weld will be fine. In this example, I'm moving along going up the weld using an arrow pattern. Assessing the quality of the weld. Assessing the quality of the weld is a valuable skill to master and must be practiced. A test plate is the best way of trying out different combinations of voltage, wire speed, and gas flow. The following slides will show you how this process is done. Step 1. Clean the area for the earth clamp. Step 2. Attach the earth clamp. Step 3. If welding flat, hold the welding tip at about 10 to 15 degrees in the direction of travel and 90 degrees in the other direction. Step 4. If welding a fillet, hold the welding tip at about 10 to 15 degrees in the direction of travel and split the angle difference in the other way. If you're doing a 90-degree weld, have the weld tip approach the angle at about 45 degrees. Then you start running a series of welds. Change just one setting at a time, and from this process you can see where I started with mid-voltage, mid-speed in number 1, running right through 2, 3, 4, 5. I tried variables and decided that number 5 was the best weld. From there, I kept the settings the same and changed my approach, running faster and slower and trying to weld on contaminated steel. The best weld should be as thick as is specified on the drawing, be consistent in thickness and height, have melted into the workpiece on both sides of the weld, not undercut the workpiece, should sit proud of the surface, depending on the drawing, and not affect the position of the workpiece parts as it cools. This can be your best weld checklist. Thank you for watching.